Good afternoon to all. It's a pleasure for me to share some of this experience that I'll be discussing on various failures that we have observed. Please pardon me because there will be more cases of failures, geotechnical failures dealing with foundations, slopes, retaining structures, etc. The main reason why you have the failures, you have many times inadequate soil data, or even if the data is adequate, it's not accurate, it's inaccurate data. The reason being we have number of soil investigation agency not having the standard equipments, standard procedure as per the code, and unless you carefully check it while selecting the agency, it can result in this particular problem. The imposed load not considered adequately, and the failure is due to that. Some of the wrong design concepts, inadequate or improper dewatering, which leads to several problems. Slope erosion, because the earth selected for embankment or for a dam is not of the right type, it is erodible, and then if it is not protected properly you can have severe erosion, and few unexpected situations which we will see through the series of slides. First I will brief you about this inadequate soil data. We had a major difficulty for one of the plant in Visakhapatnam. I'm sure some of you are from Vizag and can identify this plant. It is steel plant at Visakhapatnam, SR steel plant. What you see is only a single story office building in the front, but the main plant behind is 30 to 40 meter high roof or on steel structures. And if you go today, the plant is having a phase 2 on the other side extended by the same length as here. This picture was taken when phase 1 was over. I am showing you only this picture for this project, where when the plant was about to be commissioned, the interior painting works, electrical fittings, flooring, everything was over, and they noticed that the plant is settling at the rate of 1 millimeter per day. There is a soft clay in Vizag in this area, and pile foundation was provided, but pile foundation termination was not adequate. When after soft clay for about 10 to 12 meter, when they reach a layer of stiff clay with gravel, they mistook it as a rock layer and terminated pile in this layer. Obviously the bearing pressure that you expect from this was not adequate to take the heavy load, and all the columns of the plant were supported on that same stiff clay layer. Had the pile been taken another 3-4 meters, the rock was available there. That is what the designer had intended, that pile should penetrate 3 times the diameter in rock, but without reaching rock it was terminated in soft clay. I am not going into the detail of soil profile and how strengthening was done, because each of the column had a unique requirement for underpinning. I had a help from our colleague in structures department here, Professor P.K. Arvindan, who is now stationed in Cochin and he is a busy consultant. He designed every connection of old pile and new pile with the new pile with the old pile cap, so that the force is transmitted to the from the column, it is transmitted to the new piles. So I will not go into more detail, but if you have any question, I will answer it later on this. We go to some of the dewatering difficulties. This site is very common many places, including in our campus. I have observed when the foundations were dug up for Sabarmati hostel, there was rain and all the foundation pits were like this. If it is a hard strata like IIT campus and if it is submerged for few days in water, it does not make much difference as long as you take out the water before placing the foundation. But if it is a clay soil, as you see in this particular picture, and if the clay strata is subjected to submergence for a long time, prolonged time, what will happen? It will have reduced shear strength, it will have higher compressibility, and then you build a foundation over it, it will have a higher settlement, less bearing capacity. So this should be avoided. The first guideline given is that don't execute any foundation during monsoon. But it invariably happens that even after the foundation is dug up, there is a delay in either drawing getting approved or arrival of some construction material like steel or cement, and then it starts raining and you have this situation. This should be avoided. This is another view of some of the larger size foundation. It's for a small power plant. What you see here is not the construction water but the natural groundwater table which is at that level. And every tender which is prepared for execution of the foundation has a standard clause that groundwater shall be dewatered satisfactorily before constructing the foundation. But what normal contractor understand by dewatering is putting a small pump in a corner and pump out the water, which makes the pit empty. That is not dewatering. If you do that, it is more dangerous because when you have high water table in the strata and you lower the water table here, the water will be seeping out from all the sides. If the main enemy for slope stability is seepage of water, you find the landslide occurring during monsoon in the hilly area. It is mainly because the water which is seeping through the slope, the shear strength is not adequate to hold the self weight, and then it gives away. So then what is the better way? If you cannot remove the water from here, you should have deep wells around the excavation and lower the water table much below the expected foundation level, at least by a few meters. Then you will have totally dry surface to work with, and there will not be any seepage entering into the excavation because all water enters only from the dewatering well, and that can improve the situation. It will not create any slides, or it can even lead to subsidence in the surrounding area. If there is any important facility like road or somebody's compound wall, it can get damaged due to this soil movement. So this is one of the better way of dewatering. If you want to make excavation to here, you can have the wells. What is shown in this slide is a device called well point system, which is a transparent, a porous tip inserted in the ground for 4 to 5 meter depth, and vacuum is applied through this, so it sucks the water from the ground and the water table is lowered as per this profile, and then you have totally dry area, right? And not by directly providing a pump at the excavation. Now, what you see in this particular picture is construction of a cooling water channel which is built north of Chennai city for the power plant to get the seawater for cooling the turbines and generator in the power plant. So in the next picture you will see the process of installing it, the work starts from one end. You make the excavation and dewatering, lower the precast element which forms the wall of the channel, and as you keep placing them, you concrete the gap between the two to make the two side integral, and start backfilling it, and you progress in one direction. Excavation, placing the material, backfilling, and the work progresses further. So here you have the picture of the same arrangement. The precast articles, precast wall elements are lowered to the bottom after dewatering. Dewatering is still on, and you can see a crane standing here which is used to lower the new precast panel down to the required founding level. Please remember, you are only less than 50 meters away from the coastline. There is a Chennai coastline is here. This is Ennur port, which unloads the coal for the power plant, which is conveyed through this conveyor to the power plant on the left side. And this cooling water being brought from the sea through this channel will be feeding to cool the turbines for the power plant. So the crane which has the crawler designed, which will transmit load intensity as much as 200 kilopascal on the foundation, if it has to stand on the sand, if there is a water table right up to that, it will sink into the ground, it won't stand. So only if you dewater with this and water table is considerably below, as you have seen in earlier picture, then only this crane can operate. As the elements are inserted and concreted, the soil is backfilled here, and you start progressing the work in this direction. Here you see a different type of material placed on the surface to enable the easy movement of the giant truck. It may otherwise sink in the sand strata. So the work what you saw in the earlier picture worked well for almost this cooling water channel was required for a length of 3 kilometers, and about 2.4 kilometers the strata was sandy, which could be dewatered properly and work could be executed. The last 600 meters stretch before the cooling water channel reaches the cooling water sump from where it is pumped to the power plant, there was a change in the strata, and you don't see any sand here. This is all marine clay, dark grey in color with very low permeability, and the water table is still at the same level. And you find that because of the clay, though the same dewatering system was provided, it did not yield any result because certain minimum permeability is required for dewatering system to pick up the water from the ground. And since it was not successful, you find water at the surface of the excavation here, which was pumped, like I was telling, to keep the area dry. When that is done, the crane which was required to stand here to lower this precast element down for construction, it could not operate here because ground was so soft that the crane will sink into the ground. Second problem, the self-weight of each of these panel, which is about 1.5 meter in length in this direction, 9 meter high, it weighs about 10 to 12 tons, and it is on a limited base area about 1.5 meter by 1 meter. The ground was too soft to support it. As a result, you find that when they were arranged, you find some are sunk more, some are even tilted, either outward, inward, or towards the further excavation, resulting in a gap between the two elements. It should be tightly fitting, then only the joint will be proper. After placing these two elements, the reinforcement steel projecting, additional steel is provided, and they are integrated by casting a monolith concrete slab at the bottom. So, two problems to be solved. One, you must keep this panel in position without tilting to concrete this base slab. And second thing, a crane to operate in this location to lower this piece down. So, what you see here is the solution adopted. You see a seat pile driven in this fashion here, filled up with sand to 2 to 2.5 meter height, so that crane can come here. Now that you have a sand pad surrounded by seat pile, it is adequate to carry the weight of the crane and the elements could be lowered. This solved the problem of crane operation, but then it resulted additional operation of driving seat pile, filling it with sand, and after certain panels are installed, you have to remove this again and shift it few meters away to lower the further panel. So it resulted in extra efforts and extra cost and extra time to complete the stretch. When you design a retaining wall, you take certain soil parameter to work out the earth pressure putting on the wall. And for this wall also, depending on the borrow soil expected, the earth pressure was worked out. It is assumed, or a designer assumes, that backfilling is done in a controlled fashion in layers. What does the specification say? Do you remember? The soil should be placed in layers not exceeding 200 to 300 millimeter height at optimum moisture content and compacted with a number of passes of rollers, 6 or 8 or 10 passes depending on the type of roller. Okay. Whereas what you see in this picture is the dumper truck brings the material, it tips here, and the dozer just pushes it into the gap between the wall and this. It rolls down the height of 6 to 8 meters. No compaction at all at the deeper level. The space does not permit you to take a roller down then and compact it, right? So if the designer had foreseen this condition, he would have assumed lower strength parameter to work out the earth pressure. Otherwise, the earth pressure can be 2-3 times more compared to what it is for a compacted soil. This type of excavation is very common in the city now for every of the CMRL station construction. You have a diaphragm wall along the perimeter of the station, and you have either struts or anchors or a slab cast in the top-down method to support the wall, and the excavation goes several meters. This is not railway station, it is a facility called wagon tippler in a port where the bulk material like iron ore or coal is brought by the railway wagon over this. These columns will be supporting the rail line, and when it comes to the central portion, the entire bogie of the wagon is inverted by rotating it 180 degree. So the material falls in a hopper which is taken through a conveyor to the either stacking area or directly to the ship for loading it into the ship. This facility needs excavation to about 15 to 18 meter below the ground. And to enable this excavation, you can see RCC diaphragm wall is provided all along the excavation perimeter of the excavation. And the diaphragm wall is supported by struts, not at one level, but 1, 2, 3, and there is one more level strut, 4 levels to maintain the bending moment within the whatever section can take. There was no problem in the performance of the diaphragm wall as such. Work was going on smooth. Only thing is the dewatering which was planned to cast the bottoms there. They were already behind schedule, and site is always in a hurry to show the progress. In spite of dewatering from the external pumps, which is along the perimeter outside, the water table could not go beyond 6, 7, 8 meters, whereas it was required to go to 15-meter depth. So somebody advised, why not we put pump in the excavation and directly pump it from the excavation to make the dewatering, like what I said earlier should not be done. So when water was pumped directly from the pit, there was a level difference between the inside water, which was 15-meter depth, and outside water was about 6-7 meter depth after dewatering by the pump. Otherwise, water is close to the ground level. I forgot to mention, this is at Paradip port, where strata is sandy, as you see, and it's hardly few meters from the sea, so it is, water table is very high. So with the water level difference between the outside water and inside, there was an inward seepage of water in large quantity, and along with the water, even sand particles started flowing into the excavation. So this has created a subsidence in this area where a building is already erected. This is a controlled building which controls the conveyors to take the material, when to stop it, at what speed it operates, etc. And this controlled building has sunk 200 to 300 millimeter, creating cracks in the wall panels and some of the structural elements of beams and columns. So they realized the problem by seeing the cracks, subsidence, and some of the strut, as you see in this picture, it's not in its original shape, it has tilted, right? A strut which is designed for a compression, if there is any tilt or eccentricity in that, it can buckle and fail, right? So it was worried that if the strut buckles and fails, that will make the diaphragm wall also to fail and the excavation will collapse. So what can be done in this situation? The problem came because water was pumped out from inside. So they started getting the truck and pouring water back to the original elevation. So the inward flow has stopped. Then the outer dewatering wells were doubled in number, and only outer wells were operated so that there is no inward seepage creating this problem, and the work was completed. CMRL station building, any of the building you go and see, you will find that water is not allowed to pump from outside. It's one of the requirement in the tender that you cannot lower the water table outside the diaphragm wall. The reason being, if you do the dewatering outside the diaphragm wall, it will create settlement of the buildings in the street outside the station. So, requirement is that when you dewater inside the diaphragm wall, you must make sure that outside water table does not go more than 1 or 2 meters below the original level. So every station location, CMRL has to put piezometer in the ground and regularly record the piezometric head and show that it is not lowered, otherwise they will have to rectify the arrangement. What are the consequences if I dewater outside and if I don't dewater outside, what CMRL is insisting? Is there any change in the design? The wall is subjected to not only earth pressure but water pressure if I don't dewater outside, and that is much higher than the earth pressure. You know the earth pressure is K times gamma H, whereas water pressure is gamma W into 1 because K is 1 for water. So it will be much higher, and you have to have heavy thickness and reinforcement in the diaphragm wall if you have to design for this condition, no lowering of water table outside. Okay. The uplift force. I am showing you here only one case study. There are several instances where either the basement of a building or underground utilities in an industry is not designed for adequate uplift, which it is likely to be subjected to. And that results in many failures like this. This is only a small filtration tank in water supply plant. This is Satyasai Waterworks, somewhere in Saptagiri district. The tank was below the ground, and the brown line you see here, that is, it was embedded up to this line, and this portion was above the ground. When the soil investigation was carried out, it may be during summer where somebody reported that water table is 4 meters below the ground. So the designer thought that tank is always filled with sand and gravel bed inside and water table is 4 meters deep. So why we should worry about the uplift? It will take care of it. So no anchors or anchor piles are provided to hold the tank down under the uplift. But before the tank was made operational, just the tank is deserted from the outside, and there is heavy rain and all the hill slope in the surrounding area, the water has accumulated here. As you see, there is a standing water above ground, which created uplift, and the tank got lifted by 3 meters or so. As you see in this picture. And now it's difficult to get this tank back to its original location, right? So the filter bed is operated in a tilted position, in the moved up position, as you see here, by redoing this pipe fitting. I have here a closer view of it. The pipes which was below the ground connecting to the pipe has got moved up now. Otherwise, tank was structurally alright and not damaged because it's small in size. There are other larger underground utilities which has got damaged due to the uplift force, as you see here. This one of the effluent treatment tank measuring almost 60 meter by 60 meter, and there are 6 or 8 compartments. One of the requirement is that after the construction, it has to be shown that one side is full and the other side is empty, and there is no seepage across the wall. So when this test was being done, this being empty and this was raised to the required design water level, design storage level, you find that across the wall there is a seepage which created uplift into this, and many places there were cracks in this. There was no anchors provided here also, and more serious than that, this section is not designed as a crack-free section. When you have the moment under the uplift, if the crack width increases, you will have corrosion of the steel. And this being an effluent treatment plant, it's all that more serious that it should be a crack-free section. So then an additional layer of RCC was provided by inserting dowel all along the wall to make it safe. Okay. Lateral forces on the structure. I will be talking more about piles and pile foundation here. What you see is construction of pile foundation for a container terminal at Navaseva port in Bombay. This is famous Elephanta caves which number of tourists visit from Gateway of India. This is right in front of that hill. It's 1 meter diameter pipe at certain spacing. After installing the pipe, the pipes are covered with a precast beam element and then deck element. then in situ deck is cast over these elements to complete the structure as you see here. The work was done by Japanese firm Mitsubishi, which was operating this piling rig from a floating barge to install the pile in the ground. The work was going on smoothly, but during some cyclonic wind, a barge like this, which carries the steel and concrete to the construction location from the land, it got drifted and uncontrolled, it hit two of these piles. And the strata here is weathered rock right from the surface or near to the seabed. And as per the vertical load requirement, some 2 to 3 times the diameter penetration was required into the rock, which was provided. So the piles which were hit by this barge, it's not designed for this impact. The pile fell down, and to see what type of failure has taken place in the piles were pulled out from the water, and this is what you see here. The concrete of the pile, the reinforcement at the bottommost point, this is bottom side of the pile, that is the top. You can see all this steel here, there is no damage to it. This is bottom of the rebar cage as it was lowered down. I told you that piles were penetrating three times the diameter into the rock, but the steel liner has also gone into the rock socket. This is not desirable, if I can say it here. The overburden was hardly few centimeters, and then you have the rock. When the chiseling was carried out, it makes a rough socket to the 3 times diameter. So bore was made to 3 times the diameter. Are you able to read this color? 3 times the diameter. And then the steel liner which was provided, as you see in the picture, is here. The steel liner has penetrated If this penetration was not there, concrete would have strongly bonded with the rock surface. That could not take place. To ensure that liner goes inside, the borehole is made little larger and the liner has penetrated. You can see the liner thickness is about 6 to 8 millimeter, and it is forced into the borehole. So the remaining length over which the concrete had a strong contact with the rock was very small, and it could not withstand the moment coming due to impact. So pipe fell down, and the reinforcement bars did not have enough development left out portion where the movement has taken place. So this could have been avoided had the liner stopped at a higher elevation without penetrating into the rock. Okay, but we go back to the next slide. For further construction of the foundation, steel bracings were provided as soon as the pile is completed to see that such damage do not take place, and only after the deck work was completed that steel bracing was removed. So it's an extra factor of safety against such damage to the pile, because the cantilevering length was large and socket length was less because rock is at higher level. Okay, this is another failure of the foundation. What you see here is a cooling water sump where the seawater is brought in and then to the power plant to cool the turbines. This is in South Tamil Nadu. What you see around the perimeter of the excavation is not piles. It is only a steel pipe which is used as a seat pipe to support the clay strata to make the excavation here. The strata has sand for about 6 to 8 meters, followed by soft clay to 6 meters. Total depth is about 15 meters. Because of soft clay at the bottom of the sump, the entire sump is supported on RCC piles as you see here. The piles were constructed before excavation started by a rig like this. It's a rig for installing driven cast in situ pipe. Before the excavation started at required locations, piles were, this casing pipe was driven, gauge was lowered, and concrete was poured only up to the required level, not up to the ground level, because anyway it's going to be excavated. In the portion where sand is there, dewatering is carried out by the same well point system. You can see these are the well points. This is the header pipe which is brought to the suction pump as you see here, and the water is discharged to a safe distance away. With dewatering in sand strata, open excavation like this could be done. But as I was telling you earlier, in clay it is difficult to dewater, and therefore this additional support of steel pipe was required. So these pipes of about 600 millimeter diameter, almost touching each other, are driven to act as a cantilever seat pipe and then support this clay strata to permit excavation to the required 14 to 15 meter depth. When the final excavation was reached, the pile which was cast earlier got exposed. It was trimmed to the required cutoff level, and then the reinforcement cage is PCC is placed, and the bottom slab was to be cast. This withstood well for most of the perimeter, except some 5 or 6 meter length here, due to either a poor strength of the soil here. It could not withstand this pressure, and over a distance of 5 to 6 meter, these piles moved inward by 1 to 2 meters because of the earth pressure. And what happens at the ground level because of this movement, you can see here. This is the portion where the pile gave up. It tilted almost by 45 degrees here, and in order to enable to complete this work here, these piles are cut at this level, and it is temporarily supported by sandbags as you see here. The piles which were already completed, you can see these 2 piles. These were supposed to be in line with this other piles. But when this pile was pushed inward, the completed RCC pile also moved by 200 to 300 millimeter due to the thrust given by the soil. And a pile, concrete pile, if it has moved 300 millimeter, it would have definitely cracked at a lower level, because it is standing there. If it is elastic bending, it would have come back, right? So to check whether it's really damaged or not, integrity tests were carried out, and it confirmed that there are cracks in the pile. So they decided to cancel these piles or redo these piles. So because the pile is there at this location at a deeper level, you cannot install the pile at the same level. So the new piles in the original alignment of the row is done in between this. This was the original row, but because this pile has moved here, the compensation pile is done in between these 2 piles, and some 4 or 5 piles had to be redone before the concrete slab is cast to complete the work. Similar lateral movement is possible even due to the earth filling. This is again, I am going back to the Navaseva port, where piling work for a structure called Port Craft Berth is in progress. Earth filling is also simultaneously in progress to unload the cargo from the berthing structure. This area is being reclaimed. It has such a soft clay that under the weight of this reclaimed soil, the ground was moving towards the sea because of unstable slope, and that was creating lateral deflection of these piles before it gains the strength almost 100 to 120 millimeters. The tidal range is very high, so what you see in the picture is during low tide. During high tide, water comes right up to here. So what was done is, you can see the bracing provided, steel bracing element here and cross element in one direction as well as in the other direction, so that it acts as a rigid frame, and the lateral deflection were reduced after these bracings were provided.
Whether that will create any uplift, level variation?
Which level variation?
See,
Tidal variation? No, it does not, because piles are an individual element. There is
but
no.
the associated structures all are connected.
It is connected by a thin section. Water can go on either side of it without creating any uplift. If there is a steel plate there, it can, but there is no closed bottom there. It's open to right. So there is no danger of uplift due to this. So when you do a reclamation work on soft clay, this is what can happen. The dumper truck brings the soil, it keeps on dumping, and you find that due to soft nature of the strata below, you have a slope failure. This mass is not only going down, it's moving away. And if you see even in the water body, what you see here was earlier water only here. Because this reclaimed soil has sunk down, the soft clay along this edge has heaved up there, and it has come out from the water, right? And as you keep filling the soil further here, this portion of the heaved up clay will be moving away in the radial direction. This movement of the heaved up clay in the direction of filling is called mud wave. So as you keep filling, there is a mud wave created which moves in the direction of filling, and that created a big problem to the structure which was built here. This another interesting thing. There are two parts to be built to make this container terminal ready. One is the spile which you saw the Mitsubishi crane operating to complete the piling and the deck over it. And there is a piled approach up to certain depth in water, and beyond which it was an earthen bund and the reclamation of the land. So two separate contracts were given, one for the pile supported deck, the other one the earthen bund and the reclamation. Because we don't need Mitsubishi to do the earthwork. That was by a local contractor. While framing the work schedule, it was thought that the earthwork will be completed first, and Mitsubishi will be able to use this approach to complete some of the piling work from here. But it so happened that there was delay in finalizing the earthwork contractor, and Mitsubishi's work completed first. So they completed Is there any? It's okay. Mitsubishi completed the piling work, this was still not over. So they completed the piled approach, and when this earthwork was in progress, this soil started moving in the radial direction, and it has hit the first two piles, the mud wave. It has created lateral force on these piles and damaged those two piles. So if you see in the next picture, so these two piles, what you see in the front of the completed deck, moved inward by the mud wave and made the pile out of the plumb, and it created cracks in the joint between the pile and the pile cap. So it was necessary to strengthen that end, and you see that 3 new piles are installed there. You are able to see 1 pile in between and 2 on the either side. That is replacement of the last 2 bay pile which got tilted and damaged by this mud flow. So my colleague from Ocean Engineering, Professor Sundar Vadivelu, who is structural engineer, he has given the design of the 3 replacement pile in place of these 2 damaged pile, and then the earthwork was completed. I don't know whether you are able to see the crack at the joint between the pile and the cap. It has a clear gap created because maximum bending moment occurs at that joint. Then the dispute, whose fault it is. Mitsubishi say, I cannot install the 3 additional pile because I have completed my work, and the damage is due to the mud wave for which I am not responsible. The earth moving contractor says the shear strength given in the tender is different, and so they are checking the shear strength again of the south cliff. But anyway, the work was completed by completing the approach there. Certain more forcing loading that you expect in industrial structure. This structure, what you see here, is a urea silo. There are so many linear silo like this, which will have length 200 to 300 meter, width as written here is 55 meter, and the height of the storage at the center, it's a triangular heap. At the center it could be 10, 12, 15 meter depending on the angle of reinforce. So when you have product stacked on such a large dimension, both length and width wise, it transmits heavy load intensity on the foundation strata. The roof of this silo is anyway supported on pile foundation, which takes the load to a deeper competent strata. But it will be too expensive to support this entire floor area also on piles. So the floor is normally left on the ground, and if you do that, you have to check whether the stresses are within the tolerable limit or the structure can be subjected to any force due to that. So to verify this, in one of the fertilizer plant under construction at Kakinada, this is at Nagarjuna Fertilizer in Kakinada, similar silo was being built. So to check what are the settlements in the ground, a trial field, what you see here, was constructed. The trial field is 30 meter by 30 meter in the plan at the bottom, 15 meter by 15 meter at the top, and height is 5 meter from the ground level. Now 5 meter height is only 1/3 of what a load intensity a 15 meter high silo will have. But just to have an idea what happens under this loading intensity, the trial field was made and the settlements were monitored, as you see, with 5 settlement markers, settlement platforms along the axis of this trial field. And you see the settlement recorded. This was during 85, 87. As expected, point number 1 and 5 has a least settlement at the edge of the field, and point number 3, which is at the center, it has maximum settlement of about 225 millimeter.
What will be the reference for this measurement? Into settlement?
You have a fixed reference point away from this area. With respect to that, you take the level with any leveling instrument.
But we don't know the geography where the up to where settlement is spread.
Yeah, so if the width of this field is 30 meter, you leave another 30 meter and go beyond that and have a reference point. With respect to that benchmark, we take the settlement. And so the certain millimeter, what you see above is the plot of loading intensity. The height of the field was raised to 5 meter, and whenever there is an increase in the height of the field, there is a trigger of settlement corresponding to that. Apart from these 5 settlement point, what you see here, these 2 points are the inclinometer, which are inserted in the ground, which records what is the lateral displacement taking place in the ground under this load intensity. And see here is the lateral displacement records. The red line indicates the displacement as high as 20 millimeter on the top of the soft clay. Now this was of concern because there is a pile foundation supporting the roof very close to it, and if the strata undergoes an outward flow of 20 millimeter, it can create large lateral force and the bending moment in the pile for which it is not designed. So this is the section of the silo structure, roof supported on piles, and the possible lateral flow as indicated by the inclinometer. If this moves by 20 millimeter, the force will be so high that either the pile has to be designed for that steel with extra steel to take the bending moment, or there should be any other alternative. So what was finally adopted is that a central strip was supported on pile foundation, so that majority of the stack load, as it is marked, is transmitted onto the pile foundation without loading the soil, and only the portion, the triangular portion on 2 sides where 45 plus 5 by 2 is written, that much weight is directly going onto the soil, which has much reduced load intensity. So this resulted in additional piles, but you see as written below, the factor of safety adopted for the normal pile is 2.5, whereas the factor of safety here was reduced to 1.5 just to economize the foundation of the strip. Even if it has a differential settlement with the surrounding floor, it's not going to cause any problem, and that is why factor of safety was lowered, which could permit reduction in the pile length and adopting larger spacing between the pile.
If the stacking was not symmetric, whether it can build any settlement?
Stacking is always done from the top. There's a conveyor at the ground which discharges the material, so it is always symmetrical. Even the extraction is symmetrical with the bucket operating on both sides. But even if it is asymmetric loading, it does not create problem because there is no retaining structure here. If it's a cylindrical silo with asymmetrical loading, you can have torsion and moment coming due to that in the silo wall. I think the battery is weak. Yeah, yes. So I will be discussing about problem related to the capacity of the pile. I am telling about not structural capacity of pile. the geotechnical capacity of the pile. Many times due to the construction difficulties, you find that pile do not perform as they should perform. All the piling work nowadays is being done by rotary rig, what you see here. These rigs are having a powerful engine to apply high downward thrust, high torque, high speed to withdraw, and that's why the boring work is very fast. But unlike the regular piling rig like DMC chisel and what you have, which has the bentonite slurry circulation, this rig does not permit a continuous bentonite slurry circulation. So every time you take out a bucket from the pile hole with the cut material as you see deposited by the side, the level of bentonite in the borehole, what you see here is a borehole with a casing pipe, the level goes down by volume equal to the volume of the bucket which is taken out. If you don't carefully go on pumping bentonite back into the borehole to maintain the water table at the top, the water table, the water slurry level in the borehole will be going down, right? Second thing is, because there is no circulation, with more and more soil cut at the bottom of the borehole, the slurry becomes thicker unless you replace the slurry at constant interval. You might have read in specifications that bentonite slurry used for piling should have a density of 1.05 gram per centimeter cube. If the slurry is thicker or heavier, you should replace it with a fresh bentonite slurry. If this is not checked, then you can have a problem what is seen in this particular site. It's a power plant where this 600 millimeter diameter pipe was being constructed by this rotary rig. You can see the dimension of the bucket. It has 600 diameter and height of about 1.5 meter. When it is operating 12-15 meter below the ground, under the bentonite slurry, after cutting the material, when the bucket is lifted out with a high speed of the machine, the bucket almost acts like a piston, right? The thick bentonite slurry which is available above the bucket cannot immediately go down below the bucket through the small gap available around, and that creates a suction under the bucket, resulting in surrounding soil getting collapsed into the borehole under the suction pressure. So at this particular site, the strata was very dense silt with N value more than 50-60, and pile was designed to about 16 meter depth with certain capacity. When the load test was carried out, it failed at a load less than the design. So alarm was raised. What is the problem? Why the pile is failing at such a low load? Then it was realized that this was the problem. The bentonite was becoming very thick and suction effect was created. So the bentonite density was checked at site. You have the regular lactometer to measure the density at site. So take a sample of bentonite from the borehole, and this instrument has a scale as you see. I'm sorry, it's not facing the camera. It starts with 1.995, 1.0, and it goes up to 1.5 or 1.6, right? And as you see here, even 1.5 is 1.6 is outside the slurry mark. So the density is much more compared to what it was supposed to be. And when the bucket is pulled at high velocity, the suction was created. So two changes were made, that bentonite slurry should be replenished every time the pile reaches certain depth. And second thing is the rate at which the bucket was withdrawn from the borehole was reduced. So with these two, the suction effect was avoided and pile has improved its capacity. How much time we can? 15-20 minutes. Okay. These are some of the difficulties in well construction. When you have to construct the well foundation in water, this is construction of well foundation by creating an artificial island in the water, and then
construction site usually whether rock is really reached, any test is there.
There is no need that rock is reached. There are many wells which are terminated without rock. Earlier IRC code is insisting that well has to be terminated in rock, but we have several instances where rock is not available. The example is the Delhi Metro bridge across Yamuna River. Up to 45-50 meters there is no rock. All the well foundation for that bridge of Delhi Metro is terminated in city center. Okay. But you can do a test, you can do an SPT at the bottom of the well before the plug is cast to verify the strata. You can take sample, you can even in some case go down and inspect the strata.
Yeah, really checking shear wave velocity or what type of check?
Any type of test you can do, either it's SPT test, cone penetration test. The instrument can be taken down and tested. So, as per the guideline in well construction, you are not supposed to dewater the well. If you dewater, the same situation as that wagon tippler, that outside water table is high and water will gush into it, loosening the soil strata around it. In this particular case, you see the water table inside the well was lowered to make it to sink fast. The weight of the staining should be adequate that when you excavate the soil, it automatically goes down. But if the well is not going down, you have other methods of pushing it by anchors or creating a dead weight over it. But in this particular case, the contractor has dewatered the well for the water to gush into it, which will lose the shear strength around and the well will sink down. It will solve his problem of sinking the well staining, but it is at a cost of loosening the strata around, which will have much less bearing capacity. So just the different views of it. I will skip this. One of the major problem when you are using well foundation in bridge construction is control of tilt of the well. If the strata is very poor and you are not able to control the tilt or have uniform excavation at the bottom, you find that the well has uncontrollable tilt. This is one of the bridge near Bhimavaram where tilt was so uncontrollable that after constructing well foundation for 3 piers on either side of the creek, the contractor refused to continue further construction in the water. And then the design was modified as a pile foundation and the balance bridge was supported on pile foundation. So here you see a picture of the completed foundation where because of the tilt, the pier is eccentric. You can see eccentricity is more than 600 millimeter. Right. Fortunately, the stability with this eccentricity was okay, just meeting the requirement. Otherwise, you have to have an additional support created to make the foundation safe. Okay. This is about 15-story building in Bangalore, and just while it was under construction, what is the problem? While this was under construction, you find that all the floors in a particular corner of the building, like a pack of cards, it has come down. Right? Do you think it is a foundation problem, or it is a problem of the design in the structure? Huh? It is due to the differential settlement. What happened? These 2 or 3 columns on this corner here, a sump was required to be made, and this sump level was deeper than the footing level of these columns. There is no pile foundation for this, and when the excavation was made for the sump, due to some reason the soil collapsed, resulting in the settlement of this foundation, and due to the differential settlement between this column and it's all pre-stressed slab without any beams under, as you see in the picture, and on the floor came down. It could be that impact of the first floor fell on the second and third, but the failure was triggered by the differential settlement. These are different views of it. You can see the steel is clear. That's because it's not torch steel, it's a pre-stressing steel, and without, so it came out clear. And so then the grouting was carried out under the foundation, and these floors were reconstructed to its original form. Okay. I have further case study on failures of earth dams and slopes of the earth dams and canals. If you want me to stop in between, I will stop. This is the famous Mullaperia Dam. But you have a question?
Sir, if suppose a pile foundation is constructed and soil is prone to liquefaction, so how to avoid the forward pressure development?
The soil will not liquefy just like that. It liquefies either during construction and during earthquake, or there is a repetitive load applied, either a machine operating or even the waves in the sea can liquefy the material at the bed. Right? So during piling operation, you don't expect the soil to liquefy.
No, after it is constructed.
Okay. After piles are completed, if the strata liquefies, it does not provide any lateral support to the pile in the liquefied zone. So suppose if you have said strata which is liquefiable, and you have a pile foundation supporting any structure over it. So while designing this foundation, you don't consider any support from here, and whatever method you are adopting for analysis, either you consider the soil support only beyond the liquefiable zone, or fixity depth, whatever you are considering, it should be beyond this depth. And then you assume that pile is fixed here and then analyze it to get deflections and bending moment.
Even if the sand is below the end of the pile?
Sand may be below up to the tip of the pile, but entire length will not liquefy. If you see the liquefaction analysis, beyond 8 to 10 meter depth, the overburden stress is so high that it's unlikely to liquefy beyond that, even if the N values are low. Okay. So wherever ground improvement is used to prevent liquefaction, it's usually limited to 10 to 12 meter depth and not beyond that.
Are there any practices such that they provide any drainage pathways to?
No, the drainage pathway is provided to improve soft clay, to consolidate it and to complete the settlement. The drainage path is not provided for prevention of liquefaction. Yeah, anybody else? I think you were expecting me to have more concrete or more foundation structural of design of foundation. I have not discussed that. In fact,
So what is the solution provided for the steel plant? The first slide.
yeah, now that we have time to discuss. Schematically, what I was mentioning is there is a stiff clay with gravel which was misunderstood as a rock, and all the piles were terminated within that layer. Obviously, that did not have enough skin friction and end-bearing resistance to support the heavy load of the structure, and that is why the building had certain loads. So the new piles which were constructed are of larger diameter and terminated 3 meter into the rock. So after installing the new required pile of larger diameter socketed into the rock, the challenge was how to integrate this new pile with the existing structure, which is settling at a rate of 1 millimeter per day. So let us try to explain. Let's say this was some structure here. What is the structure? What was done is a new pile cap was constructed connecting all the piles. I have shown here only one pile. Please imagine that this is a group of 2 or 3 piles as per the requirement, with a new pile connecting the piles to this level. Still these two are independent. Structure was provided the bracket of RCC, made up of RCC, by inserting dowels into this. So while the piling work was going on and pile cap work was going on, these dowels were inserted and this bracket was cast. Still there is a gap between the two. Okay? Because the top structure is settling at 1 mm per day, the new piles are not settling because they are resting in the rock. Now, the requirement was to fill this gap, which was filled with a quick setting cement at a time for all the piles together. And once this cement has set, the settlement recorded showed the 0 rings. There was no further settlement. Okay. In fact, the span was large, and some cases core was made through the pile cap, and then the new piles were constructed through the core, wherever the pile cap dimension was large. Otherwise, peripheral 4 or 6 piles were enough. And these piles were grouted with the pile cap after this was done. So there is no relative movement between the two. Certain location where headroom was very small to take a piling rig to put additional piles, there piles were installed by static force with a hydraulic jack, 1 by 1 segment. You drive it, weld the segment, push it further down, and when it has reached the rock, it was connected to the structure. So this site was having the largest underpinning work carried out anywhere in the country and probably somewhere in the world also. Such a massive underpinning work has not been carried out anywhere to our knowledge.
In isolated footing, generally water is filled up with the water after rain. So,
In the pit, foundation.
foundation. So we have to cast around 50 columns for that foundation we have to cast. Generally we will do dewatering or we have to wait for dry.
If you do dewatering, don't do dewatering by pumping it from the surface. You must have wells. You must have wells, and if you provide the wells and pump out the water, you will have the surface dry. You have seen the crane operating at 15-meter depth below the ground. You can expect totally dry surface.
They have to make well and under gravity it should flow.
Yeah, the wells are made along the perimeter of the excavation. It can be 4 or 6 or 10 depending on size of excavation. And the ground has a permeability for water to enter into the well, and then you pump out with a submersible pump from the well, not from the excavation.
So that way so much precise planning can be done for big building. Suppose we have to construct normal building 20 by 30 meter. In that
Normal
condition,
building, if it is only ground plus 1 floor and or
G plus 4 we have to.
G plus 4, the foundation depth will not be large.
Yes.
Okay. And
2 meters.
if you are lucky, you will not have water table within that depth. But if
It depends on area, sir. Somewhere.
okay,
what-
if water table is there, you have to dewater,
the-
whether it is small building or big.
So what would be the case for clays? Even if you give the peripheral wells, permeability of the clay will be very less, right?
In clay soil, you have a different method of dewatering. It is called this is exactly what I was telling you should not do. In excavation in clay, you allow the water to seep through the side and allow filtering. So the water table will be gradually going down like this. It will come out from the lower reach of the slope. It will get collected in the peripheral pit. If you see the plan of the excavation, you collect all the side drain a suitable gradient in one corner. From where you provide a pump and take it out. In case of clay, even if there is a water seeping out, the stability will not be a problem. The clay, when it is stiff with a low permeability, the quantity of seepage is less, right? And it will not create a stability problem. Whereas sand, even with a slight seepage, the slope will give away because it does not have a cohesion to bond the particles together. So there the seepage is more. Any other question?
Sir, can you explain the procedure of driving the pipe through that machine? You were saying that bentonite slurry has to be, this spirit weight has to be checked every time because it should be less than like 1.05 gram per cubic centimeter. So please explain that procedure.
The bentonite powder is mixed with water. You can decide the density what you want by having the proportion between water and the bentonite. When you make a fresh bentonite slurry, it can have a density of about 1.05 if you have used the right proportion. But what happens with time when more soil is cut by the piling machine? The cut soil gets mixed with the bentonite slurry and that increases the density. So you are only measuring it. If it becomes more than 1.1, then you are supposed to dispose that bentonite and make a fresh bentonite. You may be knowing that a bag of bentonite costs as much as a bag of cement. And if the contractor is trying to save the cost by not replacing the bentonite slurry, it will become thicker and thicker. And then you have more problem of the suction created damage.
In case of pile foundation, 20 meter depth pile, if by doing pile test it is found that concrete is not homogeneous, then what should be the solution?
We have a method called grouting of cement slurry through the pipe. That helps more in the cavities around the pipe. But flow of grout within the concrete is not normally required because pile concreting is done by a trimmy pipe, right? So it's not, and the slump used is 150 to 200 mm slump. So it flows like a liquid, and you cannot take a needle vibrator to the left down, but the up and down movement of the trimmy pipe is sufficient to create a compaction to avoid any honeycombing. Still you can have voids where you have a lot of overlapping of the bars and the gap is not sufficient between reinforcement. Then you can have some air voids in the pipe. There is no practical way of blocking that later. Better is to go for a precast pipe where you cast it on the ground and you have better quality control and drive it. But driving is not permitted in certain area, sensitive area where noise and vibration is a problem. People have started piling sometime in some area and neighbors object to it and piling work is stopped. Then you have to switch to wood. It's also becoming more common. People becoming more sensitive to noise and vibrations than it was before. Okay, thank you very much.